Conduction and convection requires some material as a transport medium. These modes of heat transfer cannot operate between bodies separated by a distance in vacuum, but the earth does receive heat from sun across a huge distance. Similarly, we quickly feel the warmth of the fire nearby even though air conducts poorly and before convection takes some time to set in. The third mechanism for heat transfer needed no medium. It's called radiation, and the energy so transferred by EM wave is called radiant energy. In an electromagnetic wave, electric and magnetic field oscillate in space and time like any wave. Electromagnetic wave can have different wavelength and can travel in vacuum with the same speed, namely the speed of light, 3 into 10 raised to power 8 meter per second. You will learn these matter in more detail later. But you know why heat transfer by radiation does not need any medium and why it's so fast? This is how heat is transferred to the earth from the sun through empty space. All bodies emit radiant energy, whether they are solid, liquid or gas. The electromagnetic radiation emitted by a body by virtue of its temperature, like radiation by a red hot iron or light from filament lamp, is called thermal radiation. When this thermal radiation falls on other bodies, it partially reflected and partially absorbed. The amount of heat that a body can absorb by radiation depends on the color of the body. We find that black bodies absorb and emit radiant energy better than bodies of lighter color. This fact finds many applications in our daily life. We wear white or light color clothes in summer so that they absorb the least heat from the sun. However, during winter, we use dark color clothes which absorb heat from the sun and keep our body warm. The bottom of utensil for cooking food and blackened so that they absorb maximum heat from fire and transfer it to vegetables to be cooked. Similarly, a double flask or thermos bottle is a device to minimize heat transfer between the content of the bottle and outside. It consists of a double wall glass vessel with the inner and outer walls coated with silver. Radiation from the inner wall is reflected back to the content of the bottle. The outer walls similarly reflect back any incoming radiation. The space between the walls is evacuated to reduce conduction and convection loss, and the flask is supported on an insulator like cork. The device is therefore useful for preventing hot content from getting cold or alternatively to store cold content. Black body radiation. We have so far not mentioned the wavelength content of thermal radiation. The important thing about thermal radiation at any temperature is that it's not of one but has a continuous spectrum from the small to the longer wavelength. The energy content of radiation, however, varies for different wavelength. Figure gives the experimental curve for radiation energy per unit area per unit wavelength emitted by a black body versus wavelength for different temperatures. Energy emitted versus wavelength for a black body at different temperatures, radiation energy per unit length per unit area. देखो यहाँ पे क्या होएगा, पहले तो वैल्यू इंक्रीज करेगी, एक पीक पे जाएगी, फिर डिक्रीज करने लग जाएगी, है ना. नॉट दैट वेवलेंथ फॉर विच एनर्जी इज मैक्सिमम decreases with increasing temperature. The relation between lambda m and t is given by what is known as Wien's displacement law. It's very much important. आपको पता होना चाहिए इसका फॉर्मूले से भी और वैसे भी. Lambda m into t is constant. The value of constant, Wien's constant, is 2.9 into 10 raised to power minus 3. This law explains why the color of a piece of iron heated in a hot flame first become dull red, then yellow and finally white hot. तो देखो सबसे पहले कलर होगा रेड, फिर येलो और फिर होगा हॉट. जैसे जैसे टेम्परेचर इंक्रीज होगा उसके कोरस्पॉन्डिंग उसकी वेवलेंथ क्या कर जाएगी, कम कर जाएगी. सबसे ज़्यादा वेवलेंथ रेड की, उससे कम येलो की, उससे कम वाइट की. एंड और टेम्परेचर क्या कर रहा है अपना, इंक्रीज कर रहा है, वेवलेंथ डिक्रीज कर रही है. वेन्स लॉ इज़ यूजफुल फॉर एस्टिमेटिंग द सरफेस टेम्परेचर ऑफ सेलेस्टियल बॉडीज़. उनका कलर देख के आपको वेवलेंथ का पता चल जाएगा और बता देंगे कि उस बॉडी का इतना टेम्परेचर है. Like the moon, sun and other stars. Light from the moon is found to have a maximum intensity near the wavelength 14 micrometer. By Wien's law, the surface of moon is estimated to have a temperature of 200 Kelvin. Solar radiation has a maximum at length 4753 angstrom. This corresponds to temperature 6060 Kelvin. Remember, this is the temperature of the surface of the sun, not its interior. The most significant feature of the black body radiation curve is that they are universal. They depend only on the temperature and not on the size, shape or material of black body. Attempts to explain black body radiation theoretically at the beginning of the 20th century spurred the quantum revolution in physics, as we'll learn in later courses. Energy can be transferred by radiation over large distance without a medium. The total electromagnetic energy radiates by a body at absolute temperature is proportional to its size, its ability to radiate, and most importantly to its temperature. For a body which is perfect radiated, the energy emitted per unit time is given by A e t raised to power 4. टोटल इलेक्ट्रोमैग्नेटिक एनर्जी रेडिएटेड बाय अ बॉडी किसके प्रोपोर्शनल हो गया, उसका एरिया कितना है, फोर्थ पावर ऑफ इट्स टेम्परेचर. A is area, T is the absolute temperature of the body. This relation obtained experimentally by Stefan and later proved theoretically by Boltzmann is known as Stefan-Boltzmann law, and the constant sigma is called Stefan-Boltzmann constant. Its value in SI unit is 5.67 into 10 raised to power minus 8 watt per meter square per raised to power 4 Kelvin. Most bodies emit only a fraction of the rate given by equation. A substance like lamp black come close to the limit 1. Therefore, define a dimension fraction E emissivity and write H is equal to A E sigma T की power 4. Here E is 1 for perfect radiator. For a tungsten lamp, for example, E is 0.4. Thus, a tungsten lamp at temperature 3000 Kelvin and a surface area of 0.3 centimeter square radiate at the rate H is 0.3 into 10 raised to power minus 4 into 0.4 into 5.67 into 10 raised to power minus 8. This one, and it's going to be 60 watt. A body at temperature T with surrounding at temperature Ts emit as well as receive energy. For a perfect radiator, the net rate of loss of radiant energy. देखो इसमें हम पढ़ रहे हैं कि कितनी अमाउंट ऑफ एनर्जी रेडिएट हुई है, कितनी एब्जॉर्ब हुई है, एंड दैट्स H इज इक्वल टू सिग्मा A T रेज़ टू पावर 4. अगर दो टेम्परेचर हैं तो दोनों का डिफरेंस, अदरवाइज सिग्मा A T जिस एटमॉस्फेयर में वो है. फॉर अ बॉडी विद एमिसिविटी E द रिलेशन मॉडिफाइज. वैसे तो हमने फॉर्मूला क्या लिखा है, H इज इक्वल टू सिग्मा A T रेज़ टू पावर 4 का डिफरेंस, और जब हम बात करते हैं एमिसिविटी की तो ये हो जाएगा H इज इक्वल टू E A T रेज़ टू पावर 4 का डिफरेंस. As an example, let us estimate the heat radiated by our bodies. Suppose the surface area of a person body is about 1.9 meters square and the room temperature is 22 degrees Celsius. The internal body temperature we know is 37 degrees Celsius. The skin temperature may be 28 degrees Celsius. The emissivity of skin is about 0.97. For the relevant region of electromagnetic radiation, the rate of heat loss is the value of sigma, the value of E, and then temperature in Kelvin 301 की power 4 minus 295 की power 4, ये आ जाएगा 66.4 watt, which is more than half the rate of energy production by the body at rest, that is 120 watt. To prevent this heat loss effectively, better than ordinary clothing, modern Arctic clothing has an additional thin, shiny metallic layer next to the skin which reflects the body radiation. Next is greenhouse effect. The Earth's surface is the source of thermal radiation as it absorbs energy received from the sun. The wavelength of this radiation lies in the long wavelength infrared region. But a large portion of this radiation is absorbed by greenhouse gas, namely carbon dioxide, methane, nitrous oxide, chlorofluorocarbon, and tropospheric ozone. This heats up the atmosphere, which in turn give more energy to Earth, resulting in warmer surface. This increases the intensity of radiation from the surface. The cycle of process described above is repeated until no radiation is available for absorption. The net result is heating up of Earth's surface and atmosphere. This is known as greenhouse effect. With the greenhouse effect, the temperature of Earth would have been minus 18 degrees Celsius. Concentration of greenhouse gases has enhanced due to human activities, making the Earth warmer. According to an estimate, average temperature of Earth has increased by 0.3 to 0.6 degrees Celsius since the beginning of the century. Because of this enhancement, by the middle of the next century, the Earth's global temperature may be 1 to 3 degrees Celsius higher than today. This global warming may cause problem for human life, plants and animals. Because of global warming, ice caps are melting faster, sea level is rising and weather pattern is changing. Many coastal cities are at a risk of getting submerged. The enhanced greenhouse effect may also result in expansion of deserts. All over the world, efforts are being made to minimize the effect of global warming. Now the most important one, Newton's law of cooling. As we all know that hot water or milk when left on a table begins to cool gradually. Ultimately it attains the temperature of the surrounding. To study how slow or fast a given body can cool and exchange heat with its surrounding, let us perform this activity. Take some water, say 300 ml in a calorimeter with a stirrer and cover it with a 2-hole lid. Fix the stirrer through one hole and fix the thermometer through another hole in the lid and make sure that the bulb of thermometer is immersed in the water. Not the reading of the thermometer. This reading T1 is the temperature of the surrounding. Heat the water kept in a calorimeter till it attain a temperature say 40 degree above the room temperature. Then stop heating the water by removing the heat source. Start the stopwatch and not the reading of the thermometer. After a fixed interval of time, say after every 1 minute of stirring gently with the stirrer, continue to note the temperature of the water till it attain a temperature about 5 degrees Celsius above that of the surroundings. Then plot a graph by taking each value of the temperature along y-axis and corresponding value of T along x-axis. From the graph you can infer how the cooling of hot water depends on the difference of its temperature from that of the surrounding. You will also notice that initially the rate of cooling is higher and decreases as the temperature of the body falls. किसी बॉडी का टेम्परेचर जितना कम होता रहेगा ना उतना ही उसको और कूल करना डिफ़िकल्ट हो जाएगा. जैसे एक बॉडी 60 डिग्री से 50 डिग्री सेल्सियस इजीली चली जाएगी, 50 से 40 थोड़ा सा डिफ़िकल्टी के साथ, 40 से 30 और डिफ़िकल्टी के साथ, 30 से 20 लेके आएंगे तो और ज़्यादा डिफ़िकल्टी होगी. तो यही बोला है द इनिशियली द रेट ऑफ कूलिंग इज हायर एंड डिक्रीजेज एज द टेम्परेचर ऑफ द बॉडी फॉल. द अबव एक्टिविटी शोज दैट अ हॉट बॉडी लूजेज हीट टू इट्स सराउंडिंग इन फॉर्म ऑफ हीट रेडिएशन. द रेट ऑफ लॉस ऑफ हीट डिपेंड्स ऑन द डिफरेंस इन टेम्परेचर बिटवीन द बॉडी एंड इट्स सराउंडिंग. न्यूटन वॉज द फर्स्ट टू स्टडी इन अ सिस्टमैटिक मैनर द रिलेशन बिटवीन द हीट लॉस्ट बाय अ बॉडी in a given enclosure and its temperature. According to Newton's law of cooling, the rate of loss of heat of the body is directly proportional to difference of the temperature of the body and the surrounding. This law holds good only for the small difference of temperature. Also, the loss of heat by radiation depend upon the nature of surface of the body and the area of exposed surface. We can write the rate of loss of heat is equal to K into T2 minus T1, where K is positive constant depending upon the area and nature of the surface of the body. Suppose a body of mass m and the specific heat capacity S is at a temperature T2. Let T1 be the temperature of the surrounding. If the temperature falls by a small amount dT2 in time dt, then the amount of heat loss is ms dt2. Rate of loss of heat is ms dt2 by dt. Now from the equation 11.15 and 16, what we have? Where are 1.15 and 1.16? This one heat one, and that lambda t is equal to constant and h is equal to a sigma t raised to power 4. We have ms dt by dt is equal to kt1 minus t2, dt by t2 minus t1 is equal to minus k by ms dt minus k dt. On integrating we get this value. Equation enable us to calculate the time of cooling of the body through a particular range of temperature. Once we are done with the numerical, then we remember it now very easily. Now it's given in a complicated form, but whenever you will do numerical, it's gonna be much easier to remember it. For small temperature difference, the rate of cooling due to conduction, convection and radiation combined is proportional to the difference in temperature. It is a valid approximation in transfer of heat from a radiator to a room, the loss of heat through the wall of a room, or the cooling of a cup of tea on the table. Newton law of cooling can be verified with the help of experimental setup as shown. The setup consists of a double wall vessel containing water between two walls. A copper calorimeter containing hot water is placed inside the double walled vessel. Two thermometers, though the cork, are used to note the temperature of water in calorimeter, and T1 is the hot water in between the double wall respectively. Temperature of hot water in the calorimeter is noted after equal time interval. A graph is plotted between log and time t. The nature of the graph is observed to be straight line having a negative slope as shown in the figure. This is in support. Okay, time pass. Now a pan filled with the hot food cools from 94 degree to 86 degree. ठीक है, in 2 minutes. Okay, when the room temperature is at 20 degree Celsius, how long the food will take to cool from 71 to 69? देखो, एक बार पहले जाएंगे 94 से 86, फिर सेकंड केस में जाएंगे 71 से 69. एक केस में टाइम लग रहा है 2 मिनट, तो सेकंड केस में कितना लगेगा? चेंज इन टेम्परेचर पर यूनिट टाइम, दैट इज के डेल्टा टी. चेंज इन टेम्परेचर पहले कितना है? 8 डिग्री सेल्सियस, कितने टाइम में? 2 मिनट में, इज इक्वल टू के, और डेल्टा टी कितना है? 70 डिग्री सेल्सियस. द एवरेज टेम्परेचर इज़, तो देखो इसको कैसे सॉल्व करेंगे, इसके लिए हम फॉर्मूला यूज़ करेंगे dt/dt इज इक्वल टू के एवरेज टेम्परेचर माइनस में सराउंडिंग का टेम्परेचर। कर दो वैल्यू पुट, कितने का चेंज आया है 8 डिग्री सेल्सियस का, 94 से 86 ये हो जाएगा 8 डिग्री सेल्सियस। ठीक है, कितनी देर में आया है 2 मिनट्स में, ये वाला टाइम कितना हो जाएगा 2 मिनट इज इक्वल टू के। अब यहाँ पे क्या क्या टेम्परेचर थे अपने पास 86 और 90, इन दोनों का एवरेज कितना आ जाएगा अपने पास, सॉरी 94 और 86, इनका एवरेज आ जाएगा 90। तो फिर ये हो जाएगा बाय 2 और माइनस में सराउंडिंग टेम्परेचर है 20, ये आ जाएगा के 70 डिग्री से, तो इसको सोल्व करेंगे 50, दोनों को डिवाइड करो अपने आप पास आ जाएगा 42 सेकेंड्स।